Hi, in a previous video we took a look at this Fluke PM3370B that I scored on eBay for 99 bucks, and it was almost a winner chicken dinner, except that after about 5 minutes it would just power down and the screen would just go bloop and actually collapse. So obviously something's happening with the like the high voltage EHT aspect of it, or at least, you know, that's one of the things that's involved here. So let's have a troubleshoot of this thing and see if we can find the culprit, shall we? So obviously it's going to be power supply related. So we're having a look at the power supply board here, which is, you know, a fairly complicated little beast. We've got our mains input here. There's no reefer caps on the input. We've got a full wave PTC. We've got a full wave bridge rectifier. We've got the mains high voltage caps, common mode choke, and then primary side switch in here, and our main switch-in transformer, and then a big secondary side, and look at all those Nippon Chemicon caps. Oh, beautiful. Now, the first thing you might suspect, of course, is the caps. You know, electrolytic caps, famous for failing, especially on a 20-year-old scope. But unfortunately, that doesn't really fit the symptoms. Like, it works absolutely perfect for 5 minutes and then switches off, and then restarts immediately when you power it back on, and then 5 minutes. So, you know, like when you have something that fails after 5 minutes, like that's sort of like reasonably consistent. You're looking at more of, like, you know, the thermal side of things. And I've done a video before repairing an oscilloscope where, spoiler alert, like one of the diodes actually had an internal thermal failure. After a set amount of time, it was actually dying internal to the diode. Like the junction in there, like the bond wires or whatever inside was, like, you know, failing thermally when it heated up. To analyze this, yeah, you might go around with your freezer spray and stuff like that and start playing around with stuff. But of course, the first thing you want to do is a visual inspection, and I won't bore you with the details, but I cannot find anything visual on here in terms of, you know, leaking caps or anything like that, any components that are heated up, diodes that have gone brown, resistors that have overheated or anything like that. There's no blowholes in any of the parts, so I cannot find anything visual on this thing at all. And that includes the bottom side surface mount parts as well. And you can see, like, the solder thieving on those larger pads. This means that this thing has been reflow soldered, which is, you know, fairly common for these primary secondary side surface mount parts. And I've also gone around and looked at the solder joints, for example. Like a classic thermal problem might be a dry joint, and once the component heats up, then that actually causes, you know, the component expands slightly and the joint actually breaks. And I've gone around and, you know, like the through-hole ones will be the classic for this, you know, large components, large, like, you know, power components and stuff like that. But I've gone around the board. I can't see any dry joints on this thing at all. So I'm going to rule that out for this stage anyway. So step 2 would be measuring the Diodes, and I've gone and done that, so I'll spare you the boring details. But yeah, I could not find any failed diodes at all. But as I said, this is more like a thermal thing after 5 minutes kind of problem. That's what it sort of indicates. So just measuring the diodes on the board like this, I didn't expect to find anything, and I didn't. The only component that seemed to be open was this one here, and I suspect what it might be, but we might have to verify that with the schematics. I think that's a high voltage diode. Some commenters in the previous video mentioned the EHT section, and this is the tripler here. Obviously, this is our EHT driver transformer here, which will generate the anode voltage, and then that goes into the tripler here, and that will drive however many kilovolts are required for the and that goes up to, that's the nasty don't touchy in the CRT. There it is. So, but it's all discharged now. Everything's hunky-dory. But some people, a couple of people in the comments said, yeah, these Philips scopes, they are actually famous for having the tripler like arc over and fail, and then some protection circuitry kicks in or something like that. But anyway, let's jump over to the schematics, see what we can see, just get a bit more background info before we start prodding and poking this thing. Unfortunately, there are no test points, so once this thing gets plugged in, you know, it's not easy to, like, access stuff in there. So it would have been nice if they had like various, test points along the top that you could just probe. So yeah, that could be annoying. If we get desperate, attach probes, that the wires that then come out and then attach to probes later. Let's hope we don't have to resort to that though. And some commenters also talked about upgrading the memory on this thing. And here's this sample memory. There's 8 of these, 4 on the other side. And these are 2K high-speed SRAMs. And you'll notice that there's an extra 2 pins on each one of those, an extra footprint. And you might even notice up here, ta-da, jumper links, 32K/2K. These are 2K chips, and these are 8K chips over here to give you like 32K of sample memory. In theory, I think it's probably possible to simply move these jumpers over here and then populate these with the larger part. And I have checked the manual, and it does actually have the part number for the 8K parts instead of the 32K parts. So in theory that's possible, but maybe. But anyway, that's not for this video. We have the service manual here, dates from 2000. It's very comprehensive. Only 478 pages. So hats off. Unfortunately, it doesn't give a page number, it gives a section number. First section that's of interest to us is like the main system block diagram here. So like we've got the front panel board here, we've got the main processor unit. This looks like the motherboard, the base motherboard or whatever. We've got our CRT, of course, and then we've got, this looks like that's our power supply board over there. So that's one of the things we're interested in. Shouldn't really have anything to do with the drive section. I think the EHT, when you saw that thing actually collapse, that's an EHT, high voltage. EHT is extra high tension. That's a classic thing of where the EHT is dropping down and then the capacitance goes whoop, and all your image just collapses. Like, it's not like the XY drive or anything like that. So our power supply board is pretty basic stuff. We've got a line filter here. We've got our bridge rectifier there. There's a 10 volt voltage reference. There's our flyback transformer and then the rectifier and then the 5 volt regulator. It's got to have more than that. It can't just be 5 volt output. There's got to be tons of rails, especially for the analog and digital and all that. Anyway, there is a protection circuit because some people mentioned the protection circuit, like shutting it down. So it does actually have a power fail output. But I suspect that's just going off to the processor so that it tells the processor, oh, power's failing, quick, save your settings to your non-volatile RAM and stuff like that. There's a temperature overload going down into that. I'm not really concerned with that at this stage. I think there's something else. So the output from that comes into here, and that goes into our EHT converter. Aha! And that gives our negative 2.2 kilovolts there. That'd be our anode voltage, and then 6.3 volts, that's classic voltage for the heater, the filament heater. And then there's our tripler, the high voltage multiplier as they call it, and then that goes off, follow the money, as Deep Throat says. And then here's our Graticule, yep, so that gives us 14 kilovolts. Okay, so that's what we're dealing with. Yeah, there's the 2.2 kilovolts there, that's the anode voltage. So I've got a 5 kilovolt probe, so we could actually measure that. We're not going to be able to measure the 14 kilovolts output of the tripler, which some people might have suspected it is. Okay, we've got our mains input here. Here's our bridge rectifier input varistor. So yeah, like there's no bad reefer caps or anything like that. So it's nothing to do with that, and that doesn't fit the symptoms. But anyway, so this is our primary drive side here. Here's our transformer here. So it's all switching. One thing I want to do when I put this back together is the first thing I would check for is whether or not the processor is still operational, like all of the main digital power supplies are still up, and whether or not it's just an EHT failure. So I can probably get that by just, once I put it back together, just operating the controls and see if it like still responds to the rotary encoders and stuff like that, because you can hear the click, click, click. And if all that still works, I don't even have to measure voltages to know that the digital section is still working. I should be able to get some sort of, tactile feedback from that. Anyway, I'm not seeing anything in here that would shut it down. There's the feedback, of course, coming via the optocoupler here, but no, here we go. Here's our EHT converter here. There's a signal coming in here. Okay, so that actually could shut it down, I guess. I won't go through the whole topology there, but yeah, does that come from the processor? I don't know. I might have to RTFM a bit further. But anyway, we've got 58 volts high voltage there. So, you know, we can measure that point. After it fails, of course, the whole idea is that you want to hook up meters. This is where I've showed in previous oscilloscope troubleshooting videos. I think it was where that Dia one went. I had like 4 or 5 multimeters set up just to monitor all the rails, because I knew one of the rails was dropping after, you know, 5 or 10 minutes. This is a similar sort of thing. So why you need more than one multimeter? This is one of the things you might have to measure, like, you know, several things at once. And you don't want to get in there and start probing around because there's dangerous voltages and everything. So you want to like attach all your probes first and then have them all coming out to various meters, and then you can measure them all at once and just see where one drops out. So 58 volts HT, you know, if that's not happening, then your high voltage stuff over here is not going to happen. We've got a switching transistor down here, you know, so any of that fails. You know, so it could be, you know, I wouldn't rule out like a transistor failing thermally. I wouldn't rule out like diodes failing thermally. So here's our tube EHT over here, so 14 kilovolts here. So this is our tripler. So that takes, yep, sure enough, 5. That's why they call it a tripler, 5 to 14. It's near enough. So we get our 5 kilovolts here. So this is our main, this is our EHT, well, EHT converter, as they call it. So we've got a single diode here, and that creates minus 2200 volts, which then is smoothed out by these to give us, well, minus 2200 smooth out, not switching. I'd more likely suggest like thermal failures in diodes or in here or something, because there's diodes inside these high voltage multipliers here. But somebody mentioned that these actually contain reefer caps in them and they can arc over and that sort of stuff. I wouldn't rule that out. Here's all the rails. So I've got plus 5, minus 5, yeah, minus 5, plus minus 58, minus 12, minus 18, yep, plus 18, plus 12, yep. So there's lots of voltage rails there, but I wouldn't be suspecting those. I reckon, you know, there's something in this EHT high voltage section. Yes, I think this is that component that was open, but I'm going to look up that BYB412. Almost bingo. I searched for that and I got this BY8400. Whether or not that's a schematic error, because this is exactly what this is the exact diode you would have. Anyway, these are interesting beasts. So these are high temperature, high voltage parts, and they're specifically for color televisions and monitors, high voltage applications for multipliers, slot wound diodes, split transformers. So it uses a high temperature alloyed construction. This package is hermetically sealed and fatigue free, as coefficients of expansion of all used parts are matched. Interesting. The package is designed to be used in an insulating medium such as resin, oil, or SF6 gas. So they're designed to be like potted. So the BY8412, yeah, we're talking 14 kilovolts, although it's only used in the 2 kilovolt section. So here's the interesting bit, and probably why I couldn't measure this, because the BY8412 has a forward voltage. This is a forward voltage. You're used to 0.6 volts on your diodes. These are special snowflakes. This has a forward voltage of a maximum 52 volts. It doesn't even tell you what the typical is, but that's at 100 milliamps. So look, a forward voltage going up to like 45 volts. Unbelievable. So our multimeter is only going to push like a couple of milliamps through their top. So we're down here. So we don't even know what we're going to measure. I will retry that with the 121 GW. Next logical step is to reassemble it and then check, as I said, to see if the digital section is still up and running if it's just contained to the EHT section. And then that will rule out if it's a primary side mains thing. It could be primary side mains, but I remember hearing a high frequency hum when it switched off. So all these things are important. Like all these symptoms that you get, they direct where you're going to shift your focus in the troubleshooting. So in this particular case, I know it's not like a failed ESR and failed electrolytic cap in the primary side, for example. That's just not the symptom. It's something heating up or building up charge that then arcs over or something like that, and it's something in the high voltage side of things. So I'd be very surprised if it had, say, multiple faults. But it is possible that there is, say, a problem with one of the digital supplies, and then that causes the EHT, that, you remember we saw that EHT driver line coming in, or something like that. So it could be, so the digital could be failing and then shutting down the EHT and stuff like that. But yeah, that's why we need to check if this thing's still operational and doing stuff. So let's go back, reassemble it. So there's that little sucker down there. It doesn't look like any diode that you've ever seen. It almost looks like shriveled up or something, like a little sausage or something. So if we measure that, let's get in there. I think I've got that around the right way, but if I haven't, let's swap it, and you'll notice that that is open. And if we get ohms on that, there's something there, 30 meg or something, and open the other direction. That's interesting. So, but if we get a 121 GW that has a 15 volt compliance voltage, 10.7 volts, they are. And of course in the other direction we'll get zippity doodah. There you go. So, if you didn't have a higher voltage diode tester, then you wouldn't be able to test something like that. What a sneaky little buggy. You might think that's open, and you could chase a red herring down a rabbit hole thinking that that diode is no good. Of course, you could physically or lift one leg and then hook it up to your power supply and put some current through it and test it that way, of course. Those things are annoying to test. But using a regular meter, you would think that's busted any day of the week, so you got to be careful. I've got my 5 kilovolt high voltage probe here, which is 100 to 1. So I set up my scope with a 100 to 1 division ratio. I'm 500 volts per division, and we know it's negative 2200 volts. All right, so let's power it up. It's on. Hey, negative 2200 volts. We're good. All I got to do now is wait. So I'll wait for it to fail, and then if this doesn't go back, if this doesn't collapse the 2200 volts, then we know it's just the tripler arcing over, almost certainly. So I can hear the clicks as that processor encodes the knob. So when this thing fails, assuming it's going to fail, Murphy's going to give me a break, then if we can still hear that, it means that almost certainly all the digital rails, they're all still working. You wouldn't believe it, I just pressed stop. Like I was going to go for another clip and it just happened. No. The digital rotary encoder, that's dropped down to 0. Everything's gone. So the whole thing's gone. So damn it, we're going to have to probe further. Okay, I've got some more probes hooked up now. All right, so what I've got here is the yellow one, our 2.2 kilovolts. Then we've got the green one, channel 2, that's at 20 volts per division. That's our 58 volt rail there. And the blue one, that's our 12 volt rail there. So I'm measuring the 3 different rails on here, the 58 volt, the 2.2 kilovolts, which actually gets back fed back here, by the way, I just noticed that, and the 12 volt here. I'd like to probe this power HT input, but unfortunately that's a surface mount. There's both surface mount devices on the back side of the board, and the back bottom side of the board is right down in there, right down the bottom. So you can't probe that, and the board has to be in there. Unless you've got like service extender cards, there's nothing you can do about it. If you got desperate enough, of course, you have to take the board out, then which is a pain in the ass, then you've got to solder wires on, and then you've got to have them coming out, and then you've got to probe everything, and well, we're not there yet. Okay, so I've set this up to trigger when the 2200 volt rail, when it actually collapses, like we saw before. So I've got my trigger source set to either slope there, just so that you don't do a brain fart, because it's negative voltage, so it's transitioning high. Hey, we got it. There we go. I did actually turn it back to 10 milliseconds per division. I think I should have done it slower than that. But that was our 12 volt rail. That's dropping. So our 12 volt rail's switching off. Wow. That's interesting. That high-pitched squeal is annoying. So I'm going to switch that off. That we triggered on our 2.2 kilovolt. So as that transition up, you can see it hit the trigger point there, but you can see the 12 volt, that was already decaying. That was starting to decay before that. But interestingly, the 58 volt rail has been 0 all that time. So it looks like that 58 volt HT rail there is dying before we actually get our 2.2 kilovolts shutting off. And of course, if this dies, then there's no switching, there's no voltage for the primary side switching. And then of course, if this would fail first and then this would fail after. Oi, we're getting somewhere, I think. I could now set my trigger point on there if I really wanted to capture that 58 volt rail failing. Why not? I'll actually wind that back to like 100 milliseconds per division, and I'll just leave that set up. I got it. Don't worry about like any sort of like little rises like that. Probing's not perfect on this. I'm using mains earth grounding for this sort of thing. I don't actually have the ground leads from any of these probes actually hooked up to these boards. It's going via the mains earth here and going back to the power strip under the floor here and going back. So, you know, that's just for ease. Like, we're not looking at signal integrity here. Our 58 volt rail has plummeted. Once that starts happening, yeah, of course, then our 2.2 kilovolt rail starts then decaying, or negative 2.2 kilovolts starts decaying, and our 12 volt is decaying as well. So yep, that sudden drop on your 58 volts, that'll definitely do it, because there's no more volts to switch. So yeah, no more high tension. So looking at the schematic here, this is the point where we're measuring plus 58 volts VHT, which is interesting because I can't yet find that anywhere else in the circuit. It just says plus 58 volts. It doesn't have the HT on the end of it. So I don't know if that's after some sort of switching element somewhere else in the schematic I haven't found yet. The signal was coming from like power HT here. If this was like shutting off this switching, then it wouldn't, I would expect, it wouldn't shut off the 58 volts rail. The 58 volt rail would be there and it'd simply switch off all the switching transistor here and it just wouldn't switch. But our power rail's actually failing. So either there's a switch in there or somewhere else in the schematic, or if that's coming directly from the switching transformer, then it could actually be the primary side switcher failing, because we saw that the 12 volt rail was also failing as well, and this 12 volt rail is in here. That's why I was measuring the 12, the primary side of the mains, which then generates this 58 volts and 12 volt VHT on the secondary side. So if both of these are failing, maybe we have to go back and look at the actual primary side main switcher. Okay, the answer is always more probes. So I've got two different high voltage differential probes now doing the primary side. Okay, so there we go. We've got some primary side switching. The red one there is our mains input DC. That's at 100 volts per division, 330 odd volts, something like that. And we'll wait for it to drop out again. It's just to rearrange those a little bit. Hey, I got it. And there you go. That's interesting. Yeah, the primary side is still switching, but at a much lower rate, like 2 kilohertz. That's why I can hear that 2 kilohertz buzz. Yeah, you know, it's roughly 2 kilohertz odd, whereas I can't remember what frequency it was before, but it was much higher. Primary side failed, but you can see that the mains DC is still there, so it's not any of the primary rectification diodes failing or anything like that. So I'll switch that off now. And, there we go. So that means all this goodness here, we were looking at the switching across this diode here, because it was a convenient location, and yeah, it dropped in frequency, and that would affect all of the outputs, which are all of the outputs here, which are, you know, all of your voltage rails. So everything's dropping. So that includes your EHT. So looks like people who suspected that it was like the tripler failing and stuff like that, it doesn't seem to be. It's like something in the primary side of the mains switching that's going. Well, this is interesting. It's been running for 31 minutes. Never had it go nearly this long. What I did is I actually resoldered, I re-inspected it all, couldn't find anything, so I thought I'd resolder all like the power components anyway, and I put it back together, and it failed after about 4.5 minutes, but, and then I thought, I'll time this to see like, you know, if it's fairly repeatable or not. And sure enough, the second time I do it, it's still been going 32 minutes. So I don't know what the heck's going on. Anyway, it's 10 p.m. I'm going home. Well, I've come back the next day, 3 hours and 44 minutes later. I powered it up this morning and it's still going. So it's not very bright, but yeah, it's still going. Has not carked it since the very first time that I put it back together. So really, you can only deem this fixed at this point because there's no failure that to speak of that you can troubleshoot any further. So I think the next step is to basically put the lid back on, seal it all up so it's a bit warmer inside, and maybe, you know, things might heat up in there or something like that. So I don't know, it's got to be the next step. So if I put the lid on, everything works, and I leave it powered up for days, you know, a day or something, and it doesn't fail, then, well, like, what's left? I can maybe I can freeze some stuff again to try and induce failure, but it fails after turning on, which indicates that there's a heat thing. But of course, doing thermal stressing and stuff like that might be able to induce some failures, but there's nothing I can do at this point. So yeah, I'll put it back together. So maybe there's a component that's was dodgy, but it's now healed itself, maybe after some thermal stressing, because what I've done is I did freeze the active diodes and some other active components. I measured them just to make sure, you know, like they didn't go open. I've measured the ESR of every cap on their in-circuit ESR. It's a bit of trouble to actually remove every one, but I've done those in-circuit, and they all seem fine. Everything looks visually perfect. I've resoldered a lot of all the major power components, like the transformers and the devices connected to the heatsink, like some of the you know, pass switching transistors and stuff like that. So I've done those, but as I said, first time I powered it up, it failed. But then after that, boom, it's like it seems rock solid. So anyway, there's nothing more I can do. So this, unfortunately, is going to have to conclude part one. And this is just like the nature of troubleshooting stuff like this. Like, if there's no fault, then unless you can induce it to come back, there, you know, you can only speculate. Of course, I can come up with, you know, half a dozen different theories about what could cause something like this. And please, if you've got your favorite theory, leave it in the comments down below. I'll link in the schematic and service manual down below so you can have a look yourself. But it does seem to be something at least isolated to the primary side of the mains part of it. So yeah, I don't know. Leave your favorite theory in the comments down below. But anyway, it's about the journey. So I hope you found that interesting. So at this stage, it's fixed until part two. Anyway, hope you found something useful in that video. Catch you next time. Nope, the bloody thing won't fail. I've had it going for an hour and almost 2 hours now with the case on, and it does actually get quite warm on top, but nothing. So,